Hello and welcome back. This is Lecture 7 on scientific reasoning, and this is going to be based primarily on Chapter 13 in the Critical Thinking text. I also supplement with some of my own material. This Lecture 7 and my handouts within Module 4 are not sufficient for understanding the material in Chapter 13, but they are necessary. You must also read and use the text as you work through the exercises and quizzes. For this one, I want you to look especially at my handout on hypothetical scientific reasoning and the links within Module 4. Also, be sure to review the short required videos. I provide links for you to these in Module 4. Brief review here on Chapter 10 material on causal reasoning. We use Mills' methods to test for probable causes, causal factors, by explaining apparent relations between variables or events. And I want to stress apparent. Apparent means it looks like it, but we can't jump to the conclusion that two events are connected simply because they appear near each other in space and time. So what is it exactly we explain? Well, what we explain are correlations. Why? We want to explain correlated variables or events because they appear to be causally connected, although the correlation might be accidental or produced by a separate but common cause of both. Why should we care about correlations? We should care because we want to produce some events and avoid other events, or just understand what is happening. Separating causal factors from non-causal factors helps us do this. Recall that causation implies correlation. Yes, you heard that right. So if we observe no correlation between factors or events, then we have no good reason to say one causes the other. Now, correlation might be evidence of causation. So when we observe a correlation between events or factors or variables, then we have a reason to investigate a possible causal connection, but not a good reason to accept or reject a causal connection without looking for data that could confirm and disconfirm that alleged relation. It's not enough to find evidence consistent with the idea that the one causes the other, because you also have to look for what might prove it false. And I'll say more about this as we go along. In the image I have here on vaccinations and COVID cases in Israel, you'll notice this sort of correlation between the percentage of the population vaccinated in the early days of the pandemic as compared to now. And you'll see that they sort of decrease over time. I'm looking at the blue line, new cases. And we're seeing this correlation between people getting vaccinated and decreases in cases of COVID in Israel. Now, on the face of it, this chart alone is only enough to establish correlation. It is not enough to establish causation. But it's a good reason to think causation might be what explains the correlation. So chapters 10 and 13 focus on scientific reasoning, where scientific reasoning describes and explains phenomena. Phenomena is the Greek term for appearances. And in our case, that's going to be events and correlations and causes and effects. Using Mills' methods enables us to test for probable causes by explaining apparent relations between variables, possible causal factors and circumstances, and observed effects. Scientific reasoning uses hypothetical reasoning, if-then reasoning. That is, it produces and tests hypotheses. Scientific reasoning accepts or rejects hypotheses and theories based on how well they account for observations. All hypotheses must be subject to rigorous tests, or we have no justification for accepting them. Scientific reasoning requires that we use randomized controlled trials to test a causal hypothesis. But some hypotheses cannot be tested this way for ethical reasons. I'll say more about this when we look at some of the short videos I have for you. Trials are tests where you have a control group and an experimental group, and you're looking for a significant difference between them. Now, what do these tests control for? When we say control, what do we mean? We're trying to control for bias. And bias is basically any sort of prejudice or variable that compromises our accuracy. In general, a bias is something that moves you away from the truth. And we're all familiar with some subjective biases. But there are also statistical and objective biases and errors in measurement that can compromise the accuracy of our observations and so undermine the justification for our conclusions about them. Here are some forms of control. We can initiate in a study blinding, where the subjects and the investigators looking at the subjects getting an experimental drug are not aware whether or not they are getting the drug with the active ingredient or the placebo, that is, the version of the treatment that doesn't have any active ingredient. There's also this idea of randomization, and that means everybody in the study, including those in both the experimental and control group, have an equal chance of being in either group. Again, they are blind to whether or not they're in the group that actually gets the active substance you're testing. Negative controls, for instance, are groups where no phenomenon is expected. Positive controls are groups where a phenomenon is expected. It's important to understand that an anecdote, a personal story about observations under uncontrolled conditions, are really the worst things upon which to base conclusions. They are unreliable, untestable, hopelessly subjective. Okay, folks, if you have not done so already, now is a good time to watch all of the short videos in Module 4. Discussions and quizzes feature their content. It will also help you understand the references to some of the concepts and terms. In this lecture, for instance, I'll talk about randomized controlled trials, placebos, etc. Here are screenshots of what those videos look like that I'm referring to. So this is chapter 13. It's about hypothetical reasoning. It's the kind of reasoning in science which produces and tests hypotheses. It's not unique to science, but it is something science uses from logic. Phenomena. What we want to explain are appearances or events, and science aims to account for these. That is, what we observe. Data. Scientists describe and explain phenomena using testable hypotheses. In short, it's not a testable hypothesis unless it's something we could discover to be false under controlled observations. Hypotheses are bold conjectures, vulnerable to these decisive refutations, based on observations where you control for biases, cognitive and statistical, and other confounding factors. So hypothetical reasoning is going to be this: reasoning used to produce and test precise hypotheses. For instance, in the video on whether or not sugar makes kids hyperactive, the hypothesis under test is, well, sugar causes kids to be hyperactive. And what we should observe in a controlled study is that in the group of kids that get the sugar, we should see a greater amount of hyperactivity than in the kids who do not. And the kids don't know whether they got sugar. They got sweet substances, but the one group got placebo, artificial sweeteners, whereas in the other group, the experimental group, the kids got the actual sugar. And what you need to realize from that video is that so far, this study's been repeated many times. Lots of people have undergone this study. There is as yet no difference between those kids who get the sugar and those kids who do not, with respect to how hyperactive they are. There's no difference in hyperactivity, either in frequency or intensity. Hypotheses are suppositions. They are assumptions, right? Every argument has assumptions, premises. And the mere fact that it's a hypothesis doesn't make it worth believing, right? It's got to be supported by observations, logic, argument, etc. So let's think of it this way. A hypothesis in logic and science, in anything but ordinary language, where it's something like a guess, a formal hypothesis, a scientific hypothesis, is any testable claims, any claim we are able to show false, that allegedly describes or explains phenomena. And here are some from the videos. Sugar makes kids hyper. Suppose people think, for instance, that taking vitamin C prevents colds, so the hypothesis would be ingesting 1,000 milligrams of vitamin C prevents colds. Here's another. Eating garlic lowers cholesterol. People believe by taking garlic, their cholesterol is lowered. Some people notice that after they take garlic, their cholesterol is lower. The issue there, of course, is that it wasn't a controlled trial. The measles, mumps, rubella vaccine causes autism, many people believe, because it coincides with children being diagnosed as autistic right after they've been vaccinated. However, this is when, in the ordinary course of events, kids with autism are typically diagnosed, namely around 14 to 18 months, which coincides with being vaccinated. In fact, again, watch the video on this that I have on whether or not vaccines cause autism. In fact, there is no correlation between kids being vaccinated and kids developing autism. That is, no causal connection has been found. A hypothesis is not derived from the evidence to which it pertains, but rather it's added to the evidence by investigators. How? How does this work? You postulate a specific plausible hypothesis to either describe or explain something. And this is required to account for what you observe. Any hypothesis may be true or may be false, and we're trying to figure out whether we should believe it. Either way, we are not wise to accept it or reject it unless we test it. Basically, unless we test a hypothesis, we have no business rejecting it or accepting it. We remain skeptical. We say, I don't believe it, until I've got overwhelming evidence where it's best explained by that hypothesis and not some rival explanation. There's something I'm going to call a non-disconfirmable hypothesis. That's a mouthful. A non-disconfirmable hypothesis is one which no evidence can possibly refute. We've all been exposed to stories where nothing can count against the story. And I have an example of that as we go along. Scientific reasoning requires that we seek evidence before accepting any claim, hypothesis, or theory. For instance, there are angels, demons, vampires, werewolves, zombies, people say, of the world. Now, these claims about these entities require observable evidence. It's not enough to observe behavior we find consistent with demons or angels or vampires or zombies. We have to consider alternative explanations as well. Again, the burden of proof always rests with whomever makes a claim. So if somebody says that there are angels or demons or werewolves or zombies, they owe us evidence. Further, they owe us an explanation that's better than any rival explanations, say someone pretending they're an angel or a demon or a vampire or a zombie or whatever. So the burden of proof rests with the person who makes a claim, right? In a court of law, when someone is accused of a crime, it's the prosecution's job to remove reasonable doubt and introduce sufficient evidence for the jury to believe probably the most likely explanation is that the defendant did the crime. So it's not the job of the skeptical people, the people who are looking for evidence to prove something's false. Remember the appeal to ignorance? So you want to avoid these arguments from ignorance, though they have broad popular appeal. They're just backwards ways of getting at what's true. If you can accept a claim on the basis of little or no evidence, think about this, then you can just as well dismiss a claim for lack of evidence. If the best reason not to believe a claim is that there is insufficient evidence. So, I confess, I don't believe in angels or demons or vampires or werewolves or zombies, for instance. I have not seen adequate evidence to support the existence of these things. I want to come back to something I just mentioned. Beware of the non-disconfirmable or unfalsifiable hypothesis. That is, any claim which can't be shown false by controlled observations and experiment. These are claims that get asserted as true or false, but can't possibly be contradicted by any observation or the outcome of any physical experiment. Often it looks as though it is supported by any and all observations. Some examples. Through the Middle Ages, people believed that only a virgin woman, could capture a unicorn so as to harness its power. The virgin has this ability to tame one. Now, why should we believe that? How can we test that? Well, we'd have to get a unicorn, see a unicorn and see if only a virgin can capture it. Now, look, unicorns themselves are really hard to prove into existence, right? They don't just exist because we can't prove they don't. In fact, we have insufficient evidence to believe they exist. But the thing is, according to this claim, that if you want to catch one, you have to have a virgin. Certainly virgins exist, but the issue is whether or not unicorns do, since whether they exist is dubious, not as yet substantiated. We can't test this claim. Here's another. I remember after 9/11, everybody said this, people still say this, although I think we might be doubting this. Terrorism never works, people say. Well, why do you say this? Well, because, the victims of terrorism arise from the ashes and fight back or continue their lifestyle or don't live in fear or whatever, as Americans were said to do after 9/11. Nevertheless, it looks like everything supports the claim that terrorism never works. But think about it for a second. Would anything count as evidence against that? And when you can think of an example of something which might count as evidence against that, for instance, the fact that after 9/11, much of the world did turn against the United States as a hostile aggressor in the Middle East. This was a perception. Not talking here about whether or not it's true. But the issue is, often with such claims, unfalsifiable claims, claims which cannot be shown false, people can save those hypotheses from refutation by explaining away the counter evidence. Well, Americans really weren't affected by this. The world still loves Americans. Everybody wants to be an American. See, terrorism never works. So another way to get at a hypothesis which is unfalsifiable is it looks like everything confirms it, is consistent with it, and that's a red flag. Here's another one. Suffering is a necessary evil. This is something we hear since we're children. Myself, raised in the Catholic tradition, I was always upset, disturbed by the suffering of innocents, perhaps little children with leukemia, or these horrific existences that people have to endure with congenital birth defects, or the people living in war zones, children especially. There just seems to be some extra unnecessary suffering in the world. But the way people explain that away is they say, well, every bit of that suffering is necessary. It's part of God's plan. Now, notice we've got another sort of non-disconfirmable, if you like, faith-based hypothesis that preserves the original one. In other words, we have to believe that every suffering is necessary according to God's plan, which, again, we have to believe there is a plan, that God exists, that his plan entails that all suffering is only illusory, it's rewarded in heaven, etc. There's a good reason for it. In the Middle Ages, people would say things like, of the suffering, they'd say, God wills it. God wills it, right? Deus vult. The question, of course, is, would anything count against the belief that all suffering, every bit of it, even though some suffering is necessary, for building character, for instance, for appreciating the good things in life. You need some pain so you appreciate joy. Sure. But is the intensity of the suffering and the pain that many people endure, is that evidence that the suffering is necessary? I mean, couldn't God have made the world with a little less? Children born with like brain cancer and bone cancer, etc. Okay, I'll let that go. But the idea here is that these are non-disconfirmable. Everything confirms them. Nothing can show they're false. Okay, one more example, and I mentioned the term faith-based. It's not the case that all faith-based claims are non-disconfirmable, although we find among claims based on faith, either religious or secular, claims based on faith are any claims for which evidence is not required, no evidence necessary. For instance, recall the story in Scripture of the angel Gabriel visiting Mary, the mother of Jesus of Nazareth, the Savior. Recall that he announced that she was going to be the mother of the child of God, right? This divine conception. So lots of people believe that it's true that Mary is the mother of God, and the evidence we have is this scriptural, biblical story. These ancient writings somehow justify this. Now, the other thing, of course, we have to think about is what else would explain these ancient writings? Well, people wanting people to believe this mythology, right? Certainly most people in the world don't believe that Jesus is divine or the Son of God. Lots of people do, sure, sure. But the issue is, would anything count against the hypothesis? There's several here. Would anything count against the hypothesis that angels exist, that Gabriel was an angel, that Mary was the mother of Jesus, that Jesus existed, right? We can find lots of evidence that supports those claims, but nothing seems to count against it. We can't even imagine what would count against it. That's a red flag. If we can't show something's false, we have no business believing it's clearly true. Recall that evidence is information that should justify accepting a claim. But what evidence is best? Well, scientists use what's called a hierarchy of evidence to test claims about observable phenomena, to rank the quality of evidence. Hearsay, stories told by others and passed on secondhand, thirdhand, and anecdotes, personal stories, singular stories, my personal experiences. They're never enough. In fact, they're often corrupting of our judgments. Without being able to cross-examine a witness, for instance, and without compelling circumstantial evidence, we have little reason to believe what they say. In fact, lots of historical claims have this issue. There's lots of evidence consistent with claims. There are lots of stories about things that happened in history, diaries, eyewitness accounts, traditional oral histories. And yet, if we can't cross-examine those witnesses like we do in a court of law, if we can't test their perceptions, their reasonings, the quality of their observations, if we only have 1, 2, 3 eyewitnesses when we would need many independently observers, we got a reason to doubt a claim is true. We don't prove it's false because it's dubious. But the fact that we can't prove it's false, the fact that we can't really test it adequately, is a good reason to back away. Maybe it's true, maybe it's not. That's as good as it gets. This is an evidence hierarchy. It's called the hierarchy of evidence. Have a look at this. At the top is going to be systematic reviews and meta-analyses. Next is randomized controlled double-blind studies. Then there are these cohort studies, case series, case control studies. And I do get to this point where we talk about ideas, editorials, opinions, and this is only of relevant experts, people competent, people, actual authorities about the hypotheses in the fields in question. So when you look at the video on vaccines, maybe or maybe not causing autism, or sugar causing hyperactivity in children, notice that those are based on randomized controlled double-blind studies, the highest quality, the gold standard for testing, because it has these experimental and control groups where we control for biases and errors. Let me describe for you one of the many methods that get collectively referred to as the scientific method, the method for testing hypotheses, which either describe or explain observations, reality, if you will. First, we describe a phenomenon or a problem. Second, we frame hypotheses to explain it. Always imagine more than one. In fact, I recommend at least 3, right? So there's always your favorite hypotheses, those that explain based on previous observations or expectations. Plus, you need to think of, something completely different, something that also explains data, and yet it's not a version of or related to, it's different than the one you start with. Third, you want to draw implications from each hypothesis. That is, you have to predict what you will observe if it's true, and also what you will not observe if it's false. So that if you observe what you should not observe, then you should give it up. Quick example. In the case of the hypothesis, sugar causes hyperactivity in children, we've got the experimental group, the kids that actually eat sugar. And then we've got the control group, the one which doesn't get sugar. Both groups get sweet substances. Both get the experience, the perception of sweet candy. Yet, we should see in those kids that get the sugar hyperactivity. And we should see in those kids that don't get the sugar no hyperactivity or less than usual hyperactivity. And yet what we see is that in the experimental group, we see some hyperactive kids, and lots of kids aren't hyperactive also in that group. We also see in the control group the same frequency of hyperactive kids. In other words, we don't see any difference. We would not expect to see. We predict a difference in the two groups if sugar is causing hyperactivity. We don't see it. We predict no difference if it's not the sugar. And that's in fact what we see. So when we test these implications we observe, we use logic to reject or revise hypotheses. For instance, we use Modus-Tollens reasoning. Modus-Tollens reasoning, remember, if P then Q, right? If it's the sugar, then we'll see more hyperactivity in kids in the experimental group than in the control group. But we don't see more hyperactivity. And so we have to reject the hypothesis that it's the sugar. Finally, step 5, we accept tentatively, temporarily, until a better hypothesis comes along. Keep an open mind, we might be wrong. We accept tentatively that hypothesis which explains the phenomenon best. We can never be certain. What we've got is the best available hypothesis thus far, and that's as good as it gets. We don't get certainty in science. Hypothesis testing and acceptance requires relevant observations, not merely related, but relevant to whether or not the hypothesis is consistent with observations. So a hypothesis directs the search for evidence. It tells us, the investigator, what to look for and what to ignore. A hypothesis can't be proven true by the discovery that one of its implications is true. We don't prove sugar makes kids hyper by feeding kids sugar and then seeing hyperactivity. We need to see a difference in hyperactivity levels between those fed sugar and those not. And it can't be just parents observing, of course, because parents are hopelessly subjective, biased observers. That's just the way it is. A hypothesis can't be proven true by the discovery that one of its implications is true. Thinking that it does commits the formal fallacy of affirming the consequent. Remember this? Here's an example. If God answers prayers, then Jane's cancer goes away. Well, Jane's cancer went away, so God answers prayers, right? Isn't that confirmation that God answers prayers? Well, notice this argument pattern is invalid. That is, it's possible for the conclusion to be false when all the assumptions are true. Let me go through this example. Let me show you what I mean. Suppose God answers prayers is not true. Okay, what's the story here? Well, God has a plan, and even though we pray to God, for guidance, acceptance, God doesn't grant favors. God's got a plan for even people with cancer prematurely dying. It's a tremendous loss to those of us left behind, but God doesn't answer prayers, at least doesn't grant favors, allow people to live who are, say, diagnosed with terminal cancer. So let's just work with this counterexample here. The counterexample I'm using is showing that this argument's invalid because it allows a false conclusion from all true premises. So suppose God doesn't answer prayers, that's just how God is, the suffering is necessary, etc. However, we can imagine that if God did answer his prayers, then cancer could go away. I mean, certainly God could make the cancer go away. So that's true. Number 2, Jane's cancer went away. Well, suppose Jane's cancer goes away. In 20% of cases, for instance, in breast cancer cases, did you know 20% of breast cancers diagnosed by mammography go into spontaneous remission? They don't progress further, right? So we can imagine claims 1 and 2 being true and yet claim 3 being false. That's an invalid pattern of argument. It's a bad argument because of the logic alone. All the premises could be true, but the conclusion false. Don't want to commit affirming the consequent. And that's the problem with believing a hypothesis simply because it predicts something that comes true. You also have to predict what would be false and then make sure you don't see that. You want to do a test so that you would see it's false if it is. So how do you prove or test a hypothesis? Again, here are the steps. Let's focus on these first 2, describing a phenomenon or problem and framing hypotheses to explain it. Example, we see this thick cloud cover over the town. What's going on? Lots of clouds. We notice it starts raining, so we want to describe what we see. It's raining. Okay, why? It's raining because we feel and see raindrops falling from the gray clouds above us. All right, so what we're doing here is arguing, making the case that it's raining based on the evidence that we feel and see raindrops falling from the big cloud above us, right? So that's an argument. That's not an explanation. So an explanation of the raining is going to be something completely different. So again, the argument and the explanation have the same conclusion. It's raining. Now we're going to answer the question, but why is it raining? What makes it rain? So the argument answers the question, why should we believe it's raining? The explanation answers the question, okay, but what makes it rain? It's raining because water vapor in the atmosphere condenses into drops that are heavy enough to fall then to the ground. Again, what's the difference? Arguments answer, how do you know? Unlike explanations, which answer the question, why is this so? So the argument justifies believing the description, it's raining, but the explanations specify its cause or causes. So scientific explanations must feature hypotheses that have observable implications, right? And only in this way we are able to test them. So how do we prove or test a hypothesis? By looking at implications. Implications are the consequences we predict we will see, including those we predict we will not see, which if we did see, we would give up the hypothesis or revise it or consider another one. A scientific explanation specifies a probable cause of some phenomenon. You do this by proposing causal hypotheses and testing their observable implications. Again, these hypotheses need to be testable. They need to be confirmable or disconfirmable, but really, actually, both would be good. Why is that again? If you can't test a claim by making observations that support or refute it, then the claim isn't worth accepting, because you wouldn't know if it's false if you couldn't see that it's false, because it implies something, it predicts something which doesn't come true. Scientific claims can't be compatible with all possible observations. A claim needs to rule out something if it's to say anything useful. Every scientific hypothesis must imply something true and something false so we can test it. Let me make this real clear here. There's confirmation and disconfirmation, and we are actually looking for both. Focusing here on how we test implications, we use two kinds of hypothetical reasoning. And by that I mean reasoning using hypothetical claims, if-then claims, conditional claims. So we typically do the one and then the other. Confirmation involves using modus ponens reasoning when we first frame a hypothesis to explain. I'm going to go through this slowly. So the hypothesis we have is it's rained. Okay, so why should we believe it's rained? Well, here's an argument. If my car is wet, then it has rained. My car is wet, therefore it has rained. Okay, that argument's valid in form. And what it's doing is basically saying, here's this observation, and given that observation, I'm going to frame the hypothesis that what caused it is the rain. That is, I noticed my car is wet. Okay, so I think it's rained. Well, my car is wet, so I'm going to say that's confirmation that it has rained. And by confirmation, I mean something different than what we mean in ordinary language. In ordinary language, people use the word confirmation to say something like prove true. We don't prove things are true at all in logic, right? Unless we do some sort of negative proof, which is beyond the scope of this course. So in this case, confirmation involves finding evidence that's consistent with your explanation. And this allows us, once framed, this allows us to test a hypothesis. For the disconfirmation step, for the step where we are now considering what would count against the hypothesis so we don't continue to use it, we look for something like the following. So here we've got a hypothesis, we framed it, that's the conclusion of our previous rationale. Now we load that into the conditional. Notice we change up the order of things. We say now, if H, then O. Okay, so if our hypothesis is true, then we will observe a wet car. Now suppose your car is not wet. Just giving you an idea about how disconfirmation works. Suppose we observe my car is not wet. Then we must conclude by modus tollens reasoning, which is the method of denying the consequent. That's okay. We show that it has not rained. Here it is again. If it rains, then my car gets wet. If H, then O. But we do not observe the car being wet. And so that means we must conclude it has not rained. Okay, so what's up with this? Why is my car wet? Well, other explanations. The sprinklers came on. It just came through the car wash. The neighbor was watering their plants and their hose spray reached over into my car, which is not in the garage. Okay? Lots of other possible explanations here. Okay, in Module 3, where we focused on causal reasoning about causes and effects, I gave you excerpts from a film called Freakonomics, where One hypothesis, which was very strange, was being tested by an economist. And it was the idea that somehow drops in crime rates from the 80s for the next 20 years were the result, at least in part, of the legality of abortion. So if you haven't looked at that, go back and review those. So what we want to explain is the drop in crime, violent crime, property crime, murder, which was experienced roughly from 1985 to, say, 2004. And so you'll see this on this chart, where we expected, and for a short while, crime rates did increase. We expected a, sort of predictable increase over time in the frequency of these crimes, given increases in population size and density over time. We in fact saw the opposite occur. What's up with that? What happened so that the crime rate didn't stay the same or even get worse, which we expected it to do, right? We predicted it to get worse. In fact, it didn't get worse. It got better. Again, we're looking here at murder rates, robbery rates. Notice that murder rates from the 70s through the early 90s were pretty consistent on average. Robbery rates as well. And then we saw this sort of dramatic decrease in the 90s into the 2000s. So we're asking, why was there this crime rate drop in the 1990s? We want to explain this crime rate drop. And some of the possible reasons, and in this, what I'm doing with this screenshot here is showing you the several hypotheses which were introduced to explain it. Now, this is a complex phenomenon. It's no one's saying that one of those things explains it all, the entire drop. But the point is, many believed that these were the most significant causal factors, when in fact it looks like none of these were significant, although they were, to some extent, components of the explanation. It looks like something else was at work. So innovative policing, harsher sentencing, decline in crack market activity, gun control measures being enacted, a stronger economy, more police on the streets. These are some possible reasons, causal factors. And here I refer to the paper by John Donahue and Stephen Levitt in the Quarterly Journal of Economics, published in 2001. It generated a lot of controversy, but over the years it's withstood the scrutiny of experts. It's an explanation which was overlooked, but is fairly consistent with observations. In fact, it's what people predicted we would see in the absence of these other stronger factors causing crime drops. So here's an abstract from their paper. We offer evidence that legalized abortion has contributed significantly to recent crime reductions. Notice, let's be fair, they're saying contributed significantly. They're not saying it's the be-all, end-all cause of the decline. Crime began to fall roughly 18 years after abortion legalization. The 5 states that allowed abortion in 1970 experienced declines earlier than the rest of the nation, which legalized it in 1973. States with high abortion rates in the 70s and 80s experienced greater crime reductions in the 1990s. In high abortion states, only arrests of those born after abortion legalization fall relative to low abortion states. So legalized abortion appears to account for as much as 50% of the recent drop in crime. So 50%, that's a significant amount. Let's call this the Donahue-Levitt hypothesis. And here's their theory. Unwanted children, more likely to become troubled adolescents, prone to crime and drug use. Not all of them, but on average, greater frequency of such children engage in or convicted of criminal activity. These are unwanted children. When abortion was legalized in the 1970s, a whole generation of unwanted births were averted, right? So these are kids, we're calling them unwanted children because they were kids, who were not given the advantages of the rest of us. These are kids who lived in high crime areas. So we've got a whole lot of kids not born who otherwise would have been born and responsible for at least 50% of the crime rate increase, which never materialized. So this led to a drop in crime 2 decades later when this phantom generation would otherwise have come to age. Now, I want you to notice that all 5 of Mill's methods were used here to establish this, and the one which is a little unclear to a lot of people is the method of residues, and the method of residues is what explains, in part, in proportion to, observed cases. The method of residues is what explains, in part, the several factors, not just one factor, responsible for the drop in crime rate. So yeah, the increase in prison, the decrease in the crack activity, the strong economy, the policing, other reasons account for as much as 55% of the decline. But you have to explain the rest, and that's what the method of residues does. It explains the rest. And the Roe v. Wade hypothesis, the idea that legalized abortion occurred, and in proportion to the legalized abortions that did occur, we saw this drop in crime rate. Again, we don't prove the theory is true, but we find an explanation which accounts best for data. And this explanation is one which, in addition to more arrests, decline in crack activity, more police on the street, in addition to those factors, adds to the explanation, becomes a better explanation because it has these multiple factors, the fact that abortion was legalized. So before we take seriously any hypothesis or theory, we have to seek these 2 kinds of evidence. And I've mentioned these, confirming and disconfirming evidence. Corroborating evidence or confirming evidence is any controlled observation that supports or verifies a claim. Again, to verify is to find an observation, is to have an observation that's consistent with what you expect. Doesn't prove it's true. When we verify something, we are only finding data, observations that don't contradict it. That's verification. It's very weak. Finding this is not enough. It's just support, but not compelling. Verification is not proof. Sugar makes most kids hyper. Recall that hypothesis? This would be supported by observations of most kids in controlled studies actually becoming hyper right after consuming sugary substances. But this alone does not make it true. Disconfirming evidence or falsifying evidence is any controlled observation that could or does show that a claim is false. Finding this should cause you to reject the claim, the original claim. Observing that most kids do not become hyper after consuming sugary substances would show that the claim is false. Observing, for instance, no drop in the rate of crime or an increase in the rate of crime even after Roe v. Wade was passed would be a reason to reject the hypothesis that legalized abortion had anything to do with the crime rate. Reviewing here, take another look at that video, Sugar Doesn't Make Kids Hyper. There's a lot going on in there I want you to be aware of. Great examples in there. Now, confirmation is necessary. You need to find evidence that's consistent with your hypothesis. And I mean objective. At first, corroborating scientific observations, correlations, support hypotheses, for instance, like beta-carotene protects us from cancer. Again, what we need to see is that the beta-carotene consumption, as opposed to non-consumption, leads to fewer cancer rates, and that was never found. Disconfirmation disproves a hypothesis. This is important. We want to look for disconfirmation, although this sounds crazy, but we also want to consider evidence that might show we are wrong in what we believe, because we don't want to believe what's wrong. Randomized controlled trials found no difference in the cancer rates between groups of people that consumed beta-carotene and those that did not. This is a negative result because the investigator should have predicted they'd see a difference if the beta-carotene worked, which it looks like there was no difference, and so there's no reason to think it worked. So just to give you the sketch of how this looks, in the case of sugar consumption, making kids hyper, we have to frame 3 hypotheses here. Always, I did recommend this, right? So we all like the hypothesis that it's the sugar, right? But we also have to consider what else it could be. I mean, of course, the kids aren't really hyper as a possibility, but let's suppose that they do seem to be hyper by people other than their parents. Although that's a consideration. One of the hypotheses has to be according to their parents, even though their parents might be wrong. So here are 3 testable hypotheses. It's the sugar that makes them hyper. Could be the sweetness makes them happy. Again, it's not the sugar. You can get sweetness from other sources than sugar. So it needs to be that some kids don't get the sugar and we still see some sort of hyperactivity, which, by the way, we do. And third, it's the subjective reporting of parents might explain why it looks like the sugar is making kids hyper, right? Again, we're explaining the correlation between consuming sugar, kids being hyper, right? We work backwards. We see hyper kids and we go, what's up with that? But we notice also that plenty of kids got the sugar and weren't hyper. We should notice. We should also notice that kids who get artificial sweeteners are also equally, in equal proportion, hyper. So it's something else. All right, in a nutshell, on one slide, true prediction. The fact that your hypothesis predicts something that you observe, it's good, you need that, but it's not enough evidence for any one hypothesis over its rivals. So here it is, an observation O strongly favors one hypothesis over the other when the following two conditions are satisfied and not otherwise. So if H1 were true, you would expect O to be true. And if H2 were true, you would expect O not to be true. Again, these are not options. You need both of these to be the case. That is, if H1 were true, then O would be unsurprising. And if H2 were true, O would be surprising. Again, let's talk about sugar and hyperactivity. If H1 were true, we would expect, so example, if it were true that it's the sugar, if it were true that sugar makes kids hyper, we would expect to see more hyperactivity in kids who get the sugar than those who do not. And if its rival hypothesis were true, that is, it's not the sugar, let's just put out there it's not the sugar, it's something else, we would expect not to observe a difference in hyperactivity. There's something I'll call explanation freeze. We want to resist this. This is when we like the first explanation that comes along that's consistent with our observations. In fact, we often think backwards. We think, I think the reason a person's doing something, the reason parents are in a hurry for their kids to go back to school during COVID at the very end of the outbreak, before kids are even vaccinated, is they want to get the kids out of the house because the kids are driving them crazy. All right, that's a possible explanation, right? And it's one we all, being cynical, think, yeah, sure. I mean, they're tired of their kids. They want them to go to school. But it's also possible that among those parents, maybe the majority of parents, there's actually this concern among administrators and teachers as well. There's this concern for the safety of kids. We can teach them online. It's not great. But they will be less likely to be exposed to the risk of COVID, right? So that's another explanation people tend to overlook. Oh, you're just doing it because these personal motives, you want the kids out of the house. No, that's not fair. You could also be doing it because you want to, maybe primarily you're doing it because you want the kids to stay healthy or less likely to get COVID, for instance. Again, it depends on the age of the kids, etc. So explanation freeze is accepting one plausible explanation without considering and testing alternatives. And this goes to the fifth point here. We want to accept tentatively that hypothesis which explains the phenomenon best. This method of testing two or more rival hypotheses against one another is called inference to the best explanation, but it's not perfect. An inference to the best explanation is just the idea that we accept temporarily that explanation among those available, which explains data best. Again, it could be that the best available explanation is still false. Following this method, strong evidence does not support a hypothesis as much as it tells against its rivals, which don't explain as well. Inference to the best explanation only dictates that we choose the better of rival hypotheses. It's not saying the best explanation is true. Even if inference to the best explanation is useful for discriminating between hypotheses, being the best hypothesis is not the same thing as being a true hypothesis. We must already assume that one of a range of rival hypotheses is true before the rule can be applied. But none of the candidate hypotheses might be true, right? We maybe should keep looking, since the true hypothesis might not be among those alternatives. Okay, let's look at a case. I'll call this an emergency room case. An obese, middle-aged male patient complained of chest pain. He collapses at a family dinner, and he's admitted to the ER. So what we want to explain is, his symptoms. The chest pain, the collapsing. So right away we have to start thinking of hypotheses here. And I think the best way to go is to start from, what pops into mind. Maybe he had a heart attack, right? You've seen enough movies and shows, and you're aware of this sort of thing. He sort of fits the bill. Again, don't like the first hypothesis that comes along, but you can begin with it since it is common. So hypothesis one is that the guy had a heart attack. And right away you know how to generate other hypotheses. It's going to be any that aren't the hypothesis that he had a heart attack. So hypothesis two, for the sake of argument, let's call this the hypothesis that he didn't have a heart attack. It's something else. And here we could plug in all sorts of things, but do one at a time when we test this. What else could cause these symptoms? Allergic response, indigestion, panic attack, stroke, all different things than heart attacks. But we'll begin with it's either a heart attack or it isn't. Those are the two rival hypotheses. H1 predicts P, that is, H1 predicts the idea that he had a heart attack. Hypothesis 1, he had a heart attack, predicts when we hook him up to a machine that measures the electrical activity of the heart, we will expect an erratic electrocardiogram. I'll show you an image shortly. We definitely will see that if he's had a heart attack or is having one. What would we see if it's not the case? We would see a normal, non-erratic EKG. So how does the reasoning by inference to the best explanation go, where we have two rival hypotheses, we test one against the other, we want to eliminate one so we can proceed and get closer to the true one or the most likely one given data. Here's an image. Myocardial infarction is what we're talking about here, and you'd bring the guy in and you'd measure this. So if he's still having a heart attack, top left, you'd have this hyperacute phase, and that's the rhythm of his heart. You've seen these traces, you've heard them. And down at the bottom, this would be what we'd see after, so when the heart attack ceases and he's still alive, we would see a normal EKG. The one towards the bottom, the stabilized chronic phase, would be, this is a normalized EKG. So these are the two predictions. Let's take top left, hyperacute phase image versus bottom right, stabilized chronic phase. Hypothesis 1, he's had a heart attack, predicts we should see, when measured on the EKG, this hyperacute trace image. Hypothesis 2 predicts, no, we won't see that, we'll see a normal image. We won't see the hyperacute deflection on the trace. Okay, how do we infer that a theoretical hypothesis is true so far, or more plausible than its rival using a prediction over which both disagree? So H1 predicts what we will definitely see, and also we have to imagine what we definitely will not see, so we'll at least eliminate one of the hypotheses. If both predict the same thing, then it's not a good test, right? So either H1 or H2 is true. Again, this is an inference that is inductive. The conclusion can't be necessarily true because there's all these possible explanations, and of course there are often multiple causal factors. So either the guy's having a heart attack or he's not. It's something else that's causing the unconsciousness, the chest pain, right? H1 or H2. H1 is a heart attack, H2 it isn't a heart attack. Maybe indigestion. Okay, if H1 is true, then we expect to see an erratic EKG, that top left image. Now, if H2 were true, then we would expect not to see an erratic EKG. We'd expect to see a normal one. Now, notice, a normal EKG would cause us to reject the hypothesis that he's having a heart attack, and an erratic EKG image would cause us to reject the hypothesis that he's not having a heart attack, right? So what do we observe? Just hypothetical case number 4. So suppose we observe that erratic electrocardiogram. That would mean automatically we got to rule out hypothesis 2 that it's not a heart attack because we see that erratic trace. And so we would conclude tentatively, inductively, probably H1 is true. We would be using disjunctive syllogism here. That's the name of the inference rule we're using. But the idea is that we would accept H1 over H2 because H1 predicted something we would see and predicted something we wouldn't see. We wouldn't see, right? If the guy was having a heart attack, we wouldn't expect to see a normal EKG, right? So this prediction of the normal versus erratic EKG allows us to eliminate one of the hypotheses. Okay, here's Carl Sagan. He was one of the more famous popularizers of science in the 70s and 80s. Think of him as the Bill Nye of the 90s and the aughts and the Neil deGrasse Tyson we have now. His view is this, that science is the fine art of baloney detection, detecting what's BS or nonsense or doesn't make sense. And he recommends that we always spin more than one hypothesis when we want to describe or explain what's going on. If there's something needing to be explained, think of all the different ways it could be explained. Then think of tests by which you might systematically disprove each of the alternatives, right? So you look for disproof, refutation, right? You don't take an argument seriously unless you consider whether those assumptions are true, right? You look for evidence that might expose it's false or dubious. What survives? The hypothesis that resists disproof in this Darwinian selection among multiple working hypotheses, right? The working hypothesis H1 versus H2 has a much better chance of being the right answer than if you had simply run with the first idea that caught your fancy. Don't like the first explanation that comes along. Doing science requires then framing precise hypotheses subject to disproof. A knowledge-seeking process is going to be called scientific only if it proposes and tests theories that describe or explain phenomena. And this is the format you should use when you work on the exercises in Chapter 13. If you haven't done so already, please go ahead and do so. And again, for each of these scenarios, you want to consider 3 rival hypotheses, A, B, and C. And for each of them, be prepared to provide evidence which would confirm, verify, be consistent with what you observe, what you postulate, what you hypothesize, and also what would disconfirm it. You can't accept a hypothesis without considering what would count against it. Also, then you weigh the evidence, and you proportion belief to the preponderance of evidence. Here's a slide with some of the terms with which you should be familiar in Chapter 13. Review these. These are how the terms are being used in the text. And I more or less am using the terms this way as well in this slideshow. It's not the case that these terms are used differently in logic and science, but they are used differently in ordinary language. So focus on these uses for this course and any subsequent course you might take in scientific reasoning. Let's summarize here Chapter 13. Here are 4 criteria which affect whether we accept a scientific hypothesis. Recall that we accept that the aim of science is to describe and explain phenomena. Sometimes it fails, and other things might explain or describe phenomena as well. Science has a set of methods. It's more logic-based than faith-based. It is comprised of bold conjectures and decisive refutations based on testable observations. But some hypotheses are better than others. For instance, adequacy is a criterion we want to satisfy. The extent to which a hypothesis accurately, completely fits the facts it is intended to explain. Another word for this is something we call explanatory power. That hypothesis which explains best or most or all of the observations and data is going to be more adequate. And then there's something we call internal coherence or plausibility. Right, alternate stories are plausible even if only one is true. Plausible just means makes sense. There are no contradictions. Nevertheless, you can tell plausible stories about events and only one is true. So internal coherence refers to the extent to which the component ideas of a hypothesis are rationally connected, logically consistent, etc. External coherence, consistency. This is the extent to which a hypothesis agrees with others, or other well-confirmed hypotheses. We don't want a theory about the age of the Earth that says Earth is less than 10,000 years old when we have geology and chemistry and physics and even biology producing some pretty powerful evidence that it's much older than that. And this is what we refer to also as conservativeness. This has nothing to do with political ideology. It has everything to do with you want to preserve the findings from the past. New findings should be consistent with. And if not, we need to do some tests. Maybe the old theory has to go. The last criterion I'm going to focus on is something called fruitfulness. And it's useful because we want a hypothesis to suggest new ideas for future analysis and confirmation. We can invent all kinds of explanations for things that are totally useless or maybe even trivial. And so we want those so why, for instance, are people still getting COVID even though many people are being vaccinated? Well, one answer is evolution happens. The strain mutates constantly, and there are new varieties, some of which are producing particles, virus particles, that are resistant to the vaccine or the antibodies the vaccine provokes in your body. Summarizing now, 8 steps here, exhaustive. You want to design an experiment, a test that will provide independent evidence either for or against an alleged explanation. You then want to produce a set of controlled experimental conditions under which one can produce a prediction based on the explanation. Notice a whole lot of claims can't be tested simply because we can't experiment on them. We can't do a controlled experiment. And for each of those, at least scientifically speaking, we should suspend belief. Number 3, make a specific prediction that requires that the alleged explanation is correct. In the case of the patient having a heart attack or not, unconscious patient, chest pain, we need to predict we're going to see on the electrocardiogram evidence of a heart attack. By the way, we do subsequent tests. We don't just use one test to determine this. We want several independent tests. So we also can do blood tests that show whether or not someone had a heart attack. We want to run the experiment that the predicted event will occur if and only if the alleged explanation is correct. Step 5, observe that results of the experiment need to satisfy those 2 conditions. Remember, we have to be surprised and also unsurprised. If the explanation is credible, the predicted event will happen if the explanation being tested is correct. We should definitely see what we predict, and we should not see what we don't think is going to be observed. And if we do, we have to change our hypothesis to something else. Step 6, consider and test alternative explanations, at least 2, and often subsequently we have to then run the test against the new rival explanation. 7, accept provisionally. This means temporarily, tentatively. Keep your mind open to evidence against it, new theories. Accept that explanation which is most consistent with its predictions and observed experimental results. And finally, we want to reject an explanation that evidence does not support or does not require. We don't want to invent stories to save that hypothesis if we've made some predictions that are pretty clearly showing our hypothesis is wrong or flawed. And this amounts to something I've shown you already in this logic critical thinking class. Recall we talked about disproving claims, disproving conditionals, where one way to do it is to show the conditional asserts that if A, then B. On the condition that A is true, so is B. A doesn't make B true, that's something else. A implies B, which means whenever A is true, so is B. And the test is, can we imagine A being true but B being false? If so, that's a counterexample. I'll mention a few of these here. I'm going to produce counterexamples to each of these. The counterexample, again, would show that the claim is false, and so we should not accept it. Every student who confuses valid with true fails my logic course. Well, I've had students that confuse valid with true and still pass the course. Maybe they don't do so well on the test, but they still pass the course. The majority of smokers have some sort of smoking-related illness. So this is basically saying if you are a smoker, you probably have a smoking-related illness or you will develop one. Well, in fact, the majority of smokers actually do not have smoking-related illnesses. Nevertheless, smokers have 100 to 1,000 times more likelihood of developing a smoking-related illness. So we can say smoking is a cause of these illnesses, even though we can't say that the majority of smokers will have some sort of smoking-related illness. The counterexample is basically the overwhelming data. All scientists reject supernatural claims. It's a little bit simple here. All A's are B's, right? All S's are people who reject. All scientists reject supernatural claims. Well, actually, there are scientists who believe in the supernatural. There are, for instance, scientists who believe in God. And so it's just not true that all scientists reject supernatural claims. Even if it is true, most do. That's a separate claim. Some hypotheses and theories are just plain untestable, and we want to let those go. And we do want to, I remind you, be aware of the non-disconfirmable hypothesis. One of my favorite examples is the Shroud of Turin. Surely you've heard of this. This exists in the Cathedral of St. John the Baptist in Turin or Torino, Italy. And the big issue is, is this the burial shroud of Jesus of Nazareth, died some 2,000 years ago? And, the story, according to Scripture, the New Testament, is that Jesus, was the Son of God, the Son of Mary and God. And Jesus dies for our sin. He was crucified, died, and was buried. 3 days later, he rises from the dead. Okay, well, there's that story. And what people think is that this shroud is probably the piece of cloth wrapped around his body. That's how they buried people in those days. They wrapped them in cloths and put them in crypts. Now, in this case, you got to ask yourself, why do people think this was Jesus? Well, I'll tell you why. I mean, one explanation is it looks like the paintings of Jesus that many people, I was raised in a Catholic household, it looks like the paintings of Jesus we have in our houses. But here's the thing, how do they know what Jesus looked like? There's nobody that drew a picture of him. In fact, some scientists, anthropologists, sociologists, historians have looked at this and they said, Jesus was, if Jesus existed at all, he's very likely a Semitic, Middle Eastern man. Would have had, probably dark features, dark hair, probably not blue eyes, not like the images you see in, Western white imagery of Christianity. Anyway, the point is, this could be the burial cloth of Jesus. Suppose Jesus existed, was crucified, wrapped in the cloth, put in the crypt. Sure. We would expect, if we were to date, that is, establish the date of creation, the date of origin of this shroud, we would expect it to be at least 2,000 years old. However, it's been tested. Multiple parts of it have been tested, radiocarbon dated. It looks like it's no older than several hundred years. It looks like it comes from the 13th century. So we have to start asking ourselves, well, maybe it's the burial shroud of somebody. Oh, and the other thing I should mention is that a lot of people thought that at the top here where there's this blood, so it looks like blood. I mean, it's consistent with the story of Jesus being crowned with thorns and bleeding. I mean, for all we know, this could be the burial shroud of somebody else. It could also be a fraud. We have to consider that. This is what I mean by alternative explanations. Okay, let's start off. It's Jesus. It's Jesus' burial shroud. Okay, alternative hypothesis. It's not. Let me ask you this. Would anything count as evidence that it's not Jesus' burial shroud? And you say, well, it could be. Yeah, but we're trying to say it actually is. This is what people believe. They don't believe it's possible. Of course it's possible. What they believe is that it's actual. But if nothing can count against it, then we're done here. There's no reason to take this claim seriously because evidence doesn't matter. But this is evidence, right? Yeah, but it's evidence that the shroud was created or occurred, at least in the 1200s, 1300s. But it's not evidence that it was Jesus. Do you understand? Jesus came and went. Going to come again maybe in the future. That's the idea. Jesus came and went, 2,000 years ago. So we would predict that it would be at least 2,000 years old when we measured its age. We did not see that, so we should reject the hypothesis that it could be anything from 2,000 years ago when it looks like it's no more than several hundred years old. Notice that no observation can show this is not Jesus' burial shroud, since we can always explain away failed tests of its age or authenticity. To date, the Catholic Church will allow no more tests of this. Their explanation for the recent date of the linen is that, well, they tested a repaired part of the shroud. Scientists said, fine, let's go back. And by the way, there are Christian scientists that want to test this. Scientists went back and said, okay, let's test a part where the blood allegedly is, or so let's test another part. And the church said no. So we're done. We can't test it any further. We can't do decisive tests. We can't rule out any hypotheses, so it could be fraud. So the hypothesis that this is the burial shroud of Jesus of Nazareth is non-disconfirmable. That is, it can't be proven false, which is bad if we seek truth. If nothing can show a claim as false, does that make it true? No. But it does make it untestable and thus unacceptable as true. We have insufficient evidence either way. By the way, it's okay to say I don't know. Something we do not say enough is that we don't know. Here's Neil deGrasse Tyson on this. There is no shame in not knowing. The problem arises when irrational thought and attendant behavior fill the vacuum left by ignorance. This is such an important point. I don't know whether it's the burial shroud of Jesus. I don't know whether Jesus was real or the Son of God or whatever. I don't know whether it's a fraud. I'm not trying to know. I can't be certain. We don't have enough evidence. We can't go back and see the history actually happening. But what we can do is give reasons for what we think, for what we believe. And if we don't have good enough reasons to think one explanation is true over another, we should tap out. We should say, I don't know. And that's okay. It's okay to live in a situation where you don't know. You still got to make decisions. You still got to go ahead on the basis of too little evidence and make decisions. But you don't have to know. Okay, so again, for the rest of the exercises in the chapter, use this format here. You've got this problem, this thing you want to explain, and then come up with explanations, hypotheses, and test their implications. And what I'm doing here on the rest of the slides is giving you the answers to the exercises. You should take the time and go through the exercises yourself. To be clear, you really should complete all of the exercises in Chapter 13. This is the best preparation for the final, or at least that part of the final. Again, the questions are assigned randomly. That part of the final where I draw questions from Chapter 13 ideas. Be sure to use the answer key I posted within the module to check your understanding on these. This is the end of Lecture 7 for Chapter 13. This is the last lecture for the course. There will be no more for this course.